Okay, in this video I'm going to talk about my procedure for creating a mesh that can be used to accurately compute the coefficient of lift for an airfoil, and that's an O-type topology. If you're looking to create something to maybe accurately compute the coefficient of drag, generally you'll need a little bit more wake resolution, and in order to do that you would probably go to a C-type topology. All right, I've talked about that in another one of my videos, but in this case, we're going to be looking at creating an O-type mesh for computing the coefficient of lift. I've created hundreds of these meshes. I've run tons of calculations. So I really want to share with you some of my best practices for creating these grids to really get a good balance between cell count and solution accuracy. So let's get started. The first step is to create your airfoil geometry. So you can either import it or you can create it directly. We actually have a script, so I'll go ahead and pull that up. You can download it from the Pointwise GitHub page. It's called Airfoil Generator. So I encourage you to go there, download the script. You can create NACA 4 series airfoils with it, with either sharp or blunt trailing edges. And so that's what I'm going to use to create this geometry. So I'll launch that script. And there's a little GUI for it, and you basically type in the airfoil. In this case, we're going to do the NACA 2412 with a blunt trailing edge. So we'll click Create. So we've created our airfoil geometry. And really at this point, okay, once I know what airfoil I'm running, the next step is determining the flow, okay, the flow field. You know, free stream conditions, that sort of thing. What type of simulation I'm going to run. So I'm going to run a RANS calculation. We're going to use a turbulence model with wall functions, Splart-Allmers turbulence model with wall functions. I know my free stream velocity, so really what I need to compute, what I need to do next is determine for my target Y plus value what my initial cell height in the boundary layer should be. And I generally do this before I even start meshing. So what I do is I go to Pointwise's page, so pointwise.com, and I pull up the Y plus calculator, and I enter in my free stream conditions. So in this case, we're running this at 50 meters per second. It's in air. My reference length is 1 meter. Okay, that's my chord length for the airfoil. I enter in my desired Y plus value. So you know, for wall functions, we're shooting for a Y plus of between, say, like 60 and 100. In this case, we'll be using a continuous wall function for open foam, for example. That's how we'll be setting this up. So I set a Y plus value of 65. Again, really this is based on my best practices for achieving a mesh that gives you a good balance between point efficiency and solution accuracy. So once you've set that up, click Compute Wall Spacing. You'll notice we get a wall spacing of 5 e to the negative 4 meters and a Reynolds number of 3.3 million. All right, so with that information, we can now begin to create the mesh. So the first step is to select the geometry. So I've selected the 3 curves. There's a curve defining the pressure side, the suction side, and then the blunt trailing edge. And once you've selected those curves, you can create connectors on them. So I'll do that by clicking this button that says Connectors on Database Entities. And it will create 3 connectors. The connectors don't have any points. All right, they have no dimension. So the next step is to give them points, give them grid points. And so what I'm going to do is I'm going to select the upper and lower surface, and I'm going to give them 50 points. And I'm going to zoom in, and I'm going to select the trailing edge and give that 4 points. All right, and I'll just grab all the connectors and turn their points on so you can see them. So why 50 points? Again, you know, I've run enough of these calculations. It's really a good balance, okay? It's really a good balance, not getting excessively fine for computing the coefficient of lift, all right? But if you zoom in, you'll notice the leading edge isn't properly resolved, right? We really need to adjust the distribution of points to more appropriately resolve that curvature. And the way we do that is through a spacing constraint. So we can grab the spacing mask and select those spacings at the leading edge and change them. I used 1 e to the negative 3, so we're clustering points towards the leading edge. And I did the same thing for the trailing edge as well. And the trailing edge is actually a little bit different, I should mention. If I zoom into the trailing edge, you'll notice 1 e to the negative 3 is going to work. Now, what do I mean is it's going to work? Well, I have 4 points across my trailing edge. generally what I do is I like to have, at this convex corner, I like to have the facets be the same size on either side of that corner, which they are in this case. And that allows that extrusion to march nicely off of that convex corner. You can experiment with this and see, and that's how I kind of determine what my spacing at my trailing edge is going to need to be, based on the number of points and the spacing on my trailing edge. Alright, so I've got my grid set up on my airfoil surface, so I properly discretized the geometry. The next step is to create my computational domain, alright, my far field. And to do that, all we got to do is do an extrusion. We just grab the connectors, go create, extrude, normal. We're going to do a normal hyperbolic extrusion. One face, we're going to create a single domain. And the next step is going to the Attributes tab and then just kind of walking through here. Obviously, the first thing you want to do is flip the orientation so the normals are pointing out. Okay, we don't want to grow on the inside. We want to grow towards the far field. In the step size section, the initial delta S, this is going to be the value you computed using the Y+ calculator. So this was 5e to the negative 4. The growth rate, I generally change this to 1.2. Again, for these types of meshes where you're using wall functions, turbulence miles, you're looking for a growth rate between 1 and say 1.3. I use 1.2. Again, it's my best practice. It's a good balance, okay? And I found it to work. So 1.2. The next section that I wanted to talk about, even though we're not going to change any of these, there's two parameters I want to mention in this smoothing parameters frame, and that's Kinsey-Barth and volume smoothing. So Kinsey-Barth is going to help prevent the crossing of grid lines as the front is marching out of concavities, all right, concave regions. In this case, we really don't have any, so we don't need to use this. But maybe for some airfoils that have a lot of camber to them, maybe there are some severe concavities that you're going to encounter, or just concavities in general, and you may want to turn this up a little bit. Okay, so again, in this case, I've turned it off, but I've just wanted to make you aware of this parameter in case you wanted to use it in the future. The next one that's really important is volume smoothing. Again, in this case, the default is fine. To be honest, I've played with all of these values for this case, run the calculation over and over by changing these values, and it had no significant effect on the solution. Okay, but the volume smoothing is important because the volume smoothing is actually going to determine how rapidly the grid clustering on the surface is propagated to the far field, how it relaxes. And what it tries to do is the higher this volume smoothing, it tries to equalize the volume of the elements on that extruding front. And so in some instances, maybe what happens is if I'm generating, say, like a C grid, I'll turn this down to like 0.01, almost turning it off to kind of preserve my surface spacing as I'm marching out. I'll run it, okay, a few steps, I'll turn it up. I'll run it again, I'll turn it up, I'll run it again. So I'll do those extrusions in maybe 2 or 3 stages by cranking up this volume smoothing each time, okay? Again, I just wanted to make you aware of this, all right? In this case, we don't need to use it. So we're just gonna leave it at the default 0.5, okay? The next thing is the stop condition, all right? The total height stop condition. I use this basically to automatically stop my front once it's achieved or once it's reached the kind of the far field size that I want. I've run a lot of these calculations and I've played with different far field sizes and kind of their effect on the solution. And I found that a far field size with a radius that's 100 chord lengths actually works pretty good. Okay, 100 chord lengths seems like a lot. It's actually not that much. Okay, you can actually see a pretty significant change in the solution by changing that far field size. So again, my best practice, a radius of 100 chord lengths works very well. It's a good balance in terms of cell count and solution accuracy. But this total height parameter is actually going to look at the length of the grid lines as they're extruding. And if you imagine as it's extruding, these are going to kind of bend. Okay, they're going to have some curvature to them. And so you can't use a total height of 100 because it'll stop short. So generally what I found is 1.5 times that, so 150 as my total height is going to get that extrusion out far enough. All right. Then you go back to the Run tab and set up the number of steps. So I'm going to just set 100 steps, something that's pretty large, and it's going to stop automatically once it reaches my total height stop criteria. So I'll run it. You'll notice I get a warning message just telling me that the total height stop criteria was met. So we'll delete that last step, click OK, and I have my mesh. If you zoom out, you can see there's my far field. Again, the radius is 100 chord lengths. It's appropriate for this calculation, computing the coefficient of lift accurately. And we're basically done. We have our mesh. Okay, this is it. That's how you create an O-grid for an airfoil. All right. But for setting it up for some solvers, you may need to go one step further. So for example, for OpenFoam, you may need to create a 3D mesh. And really all you have to do is just extrude this one step in the Z direction, so kind of coming out of the screen to make it one cell thick. So that's what I'm going to demonstrate now. So you would grab that domain, you would go create, extrude, do a translational extrusion in the Z direction, so coming out of the screen, and we're just going to run it one step. So it's going to be one cell deep. So we actually have a block, okay? It's a one cell deep block. And then we can set up our boundary conditions. So the first thing you would do is you'd go CAE, you'd pick your solver. So we'll pick OpenFoam, and then you would pick set up your boundary conditions. So in this case, we're actually going to have 3 boundary conditions. We're going to have an airfoil surface. We're going to have the far field. All right, we're just going to use the free stream boundary condition in OpenFoam, and then we have our side. So the way OpenFoam knows it's a 2D calculation is if you set the side domains to type empty. So we're going to have 3 boundary conditions. So we'll create 3. The first one called airfoil. The next one called far field. And the last one called sides. Okay, so I'm going to just select those. I'm going to hold down the shift key and do an inclusive selection, and that'll just make sure. It's really hard to see, but if you zoom in there, I've selected just the airfoil surfaces. Okay, zoom back out. So I'm going to drop those into that airfoil boundary condition. And that's of type wall. The sides are pretty easy to select, so I'm just going to grab those and put them in that boundary condition. And they are of type empty. Okay. And then lastly, rather than rotating and zooming and picking that thin little domain on the boundary there for the far field, it's the only one left in unspecified, so I can just click that and then click add to selection and then just drop it into that far field boundary condition and change its type to patch. Okay, so all the boundary conditions are set. Really the last step is to grab that block, go File, Export, CAE, and then drop that into the Polymesh directory, and you're ready to go. Okay. So that's how you create an O-grid for an airfoil, appropriate for computing the coefficient of lift. You saw it was pretty easy, right? I mean, it's actually pretty easy, which means you could actually automate this, and it has been done. If you go to the Pointwise GitHub page, okay, there's a script called Airfoil Mesh, and this script will actually do what we've done. Although the Kinsey-Barth parameter has been set in the script, hard-coded, as well as the volume smoothing, they've been set based on kind of my experience with different types of geometries, but you can obviously go and change them, edit that, all you'd like. Before I demonstrate this, I just want to mention on my GitHub page, Travis Kerrigan, there's an OpenFoam NACA 2412 repository. This is the case for this airfoil mesh that we've just created to run in OpenFoam. In the Polymesh directory is the Pointwise mesh as well as the exported mesh. So you can download this, run it. It's set to run at 8 degrees angle of attack, a little more interesting flow. So I encourage you to download this, run it, and kind of experiment a little bit. So I'm going to run that script. So I'm going to just clean this out and run Airfoil Mesh. So the first step is generating the airfoil. So again, 2412, create that. Okay. Next is specifying my initial cell height in the boundary layer. Okay. My growth rate, 1.2, my boundary layer height, and the points around the airfoil, and then click Mesh. And it's done. It's basically created the mesh. We're ready to go. Basically, again, it's 2D, so to set it up for something like OpenFOAM, you'd have to extrude this and then set up your boundary conditions. But those are all things that could be added to the script to completely automate this process. But anyway, again, this was just to show you how to create an O-grid, all right, a topology suitable for computing something like the coefficient of lift, and kind of using a set of my best practices from running a lot of these different calculations in the past. So thank you very much.